So, good day. Today we are entering the fourth module of Metallurgy and Material Science. And in this module, we are studying different strengthening mechanisms. We already discussed some of the strengthening mechanisms in the third and second module. So, we will daily we will study the strengthening mechanisms used in materials. Then we will study about cold working and hot working process. Then after that, we will study about different alloy steels. Okay, so more specifically, we are concentrating on steel because steel is the important member for any engineering application. So we are studying about different alloy steels and what are the different alloys added to steel. So far, we only discuss about carbon and iron. Okay, carbon impurities added to iron, we form a steel material. Okay, but other than iron, carbon, we can add different types of impurities to improve the properties of steel. So we will study about the what are the different materials we use to improve the properties and how these alloying elements affect the properties of the steel. Okay, we will study about that. Then more specifically, we will study about nickel steel and chromium steel and high speed steel because these three alloy elements, nickel, chromium, as well as for high speed steel, this is very important and the application in engineering area is very high in case of this type of alloy elements. And next we will study about cast ions and some non-ferrous alloys also like bronze, brass. There are different types of non-ferrous alloys commonly we use in engineering application, and we will study about that non-ferrous alloys also in this syllabus. Okay. So these are the course outcome. We have two outcomes we can achieve from this module. And at the end of this module, students will be able to apply the basic principles of ferrous and non-ferrous metallurgy for selecting material for specific application. So after studying this course or this module, you will be able to select a material for particular application. Okay, for example, if you want to select a material to build a furnace, or if you want to make a build a material for some coating for the engine. Okay, so more specific applications, what is the best material available? We have number of materials, ferrous as well as non-ferrous materials. Okay, so by applying the theories what we studied in the last two modules, we can select a material for specific application. So that is the first outcome you get from this module. And second outcome is CO number 5, that is define and differentiate engineer materials on the basis of the structure and properties for engineering application. So we can distinguish or define the material or differentiate material based on the structure, microstructure, and the properties of the material. Okay, so by studying the microstructure as well as property and the relationship between the microstructure and property, we can select a material for specific engineering application. So these two outcomes can be developed from by studying this module. Okay, these are the course outcomes. So this is the detail about the two course outcome. The CO number, sorry, this is CO number 3. CO number 3 and 5 is not CO number 4. So you can read that CO number 3 and 5. What are the questions behind the CO number 3 and 5 in your syllabus? The first area is strengthening mechanisms. Strengthening mechanism. So we know if we take a pure material, we take a pure material, pure crystalline material. For example, iron crystalline materials. Iron crystalline material. This is a pure crystalline material. We can see the atoms are orderly arranged throughout the material. The orientation of the atoms are same everywhere. The atoms are orderly arranged throughout the material. Okay, so this is a single crystalline pure material. Pure material, there is no impurity. That is, for example, we can take iron. Iron is a pure material. Okay, and next I am going to take another material, that is steel. Steel. So this is not a pure material. Steel is not a pure material. So in steel, steel, we have iron, and in the interstitial positions of the iron, we have carbon particles. Here we have carbon particles. Okay. So in the interstitial position, we can see carbon particles. So here the impurity we added is carbon in iron matrix. In iron matrix, we add carbon as an interstitial impurity. Okay, so we know when we compare the mechanical properties of iron and steel, of course, the iron has better mechanical property than that of the steel has better mechanical property than that of iron. So how this property improved? How can we improve the properties of the steel when we compare with iron? So by adding these interstitial carbon impurity atoms into iron crystal, we can improve the property. Okay, so we will study about different such type of mechanisms which improve the properties of the materials. Okay, more specifically, we can study about steel also. Okay, so what are the different mechanisms to improve the mechanical property? When we compare the strength, what is the strength? Last class I defined strength. What is strength? Anyone? What is strength? ഒന്നുകൂടി പറഞ്ഞു കേട്ടില്ല.
മൊത്തത്തിൽ ഉള്ള ബോഡിയുടെ
resistance to deformation.
Yes, sir. Yes, very good. So the resistance offered by or resistance to deformation for a bulk material, the entire material resistance on. Okay, that is strength. What about hardness?
Localized deformation.
Yes, the resistance offered by a material against the localized deformation, localized not simple deformation, localized plastic deformation. Okay, plastic or permanent deformation. The resistance offered by a material against localized permanent deformation is called hardness, and strength is the resistance to plastic or permanent deformation for the entire material. That is the strength offered by the material. Okay, and what is the ductility? It is the measure of It is the measure of
temporary.
It is a measure of the material can deform without any fracture. Okay, how much amount a material can deform without any fracture? That measure gives the ductility. Okay, so for example, if I take a material, I take two material. Okay, material A and B. Okay, I increase the strength of or when I apply load on A, before fracture, A can elongate up to this point. Okay, but before fracture, B can elongate up to this point only. So when we compare the final material after deformation, the A has more deformation before fracture than B. Or we can say the ductility of A is higher than that of B. Okay, so how much a material can deform plastically before fracture is called ductility. That measure is called ductility. So these are the main three mechanical properties. Now, of course, the toughness also another property. What is toughness?
Energy absorption.
The energy absorbing capacity. Strength of material labs ISO test, sharp impact test.
Yes, sir.
Yes, sir.
Yes. Okay. So during sharp impact test or ISO test, what we do? We use a pendulum and we break the workpiece or sample. Okay. So what we do actually, we measure the energy carrying capacity of the material. Okay, how much amount of energy is required to break a or fracture a material? So that measures the toughness. Okay, so for example, if you take a crockery item, I take a crockery item or glass material, and I take another steel material, steel plate, a crockery plate and a steel plate. Okay, when we drop these two items, what happened? The crockery item fails without any warning, but there is no there is a little deformation for steel material. Okay, or we can say the toughness, the energy absorbing capacity of this crockery item or glass material is very low. Okay, the toughness is the energy absorbing capacity. So in this, if the toughness is very low, then we can say they fail without any deformation, or we can say that is a very brittle in nature. Okay, so most of the brittle material has less toughness, but ductile material has higher toughness. So that is also another important mechanical property. So next we are going to discuss how we can improve these properties, these mechanical properties. So this is very essential properties for a engineering material. Okay, the engineering material should have high strength, hardness, as well as ductility also is an essential one for a ductile material, but should not be very high, because these two are strength and ductility actually opposite nature, like strength and ductility. So, but there should be some ductility. If there is no ductility, then we can say that material is a brittle one. Okay, if the material is brittle, without any warning, they fail. Without any deformation, they fail. So we should not use a brittle material for engineering application. There should be some ductility for the material. Okay, and of course, the toughness also is an important factor for considering the a particular engineering material for an application. So next we are going to discuss how can we improve these mechanical properties. For that, we use strengthening mechanism. We develop some alteration or manipulations in the material, and thereby we improve all these properties. Okay, so basically the strength of the material is purely based on one factor, that is dislocation. We already studied dislocation. The strength of the material is purely dependent upon the one factor called dislocation. We already studied what is dislocation. So strengthening mechanism is the relationship between dislocation motion and the mechanical behavior of metals. Okay, so because macroscopic plastic deformation corresponds to the motion of large number of dislocation, the ability of the metal to plastically deform depend upon the ability of the dislocations to move. So when I apply when I apply a force on this material, the material plastically deform. We can see the material is plastically deformed. How this material is plastically deformed? When I apply an external force, lots of number of dislocations are developed inside the material. What is dislocation now? So
Yes, sir.
this is dislocation.
Yes, sir.
The extra half plane is produced, and this extra half plane moves along the slip plane. Okay, this is the slip plane. This one is the slip plane. Okay, and this one is the extra half plane. This one is the extra half plane, and this extra half plane move along the slip plane. That is dislocation. We can see this extra half plane is here. And this is the extra half plane. This one, and here it is this one, and here it is this one. Okay, so this extra half plane is moving, and finally is reached the edge point. Okay, so such number of many such dislocation movement results in the deformation of the material. Okay, when I apply external force, such type of dislocations move along the material, and finally an edge is created at this tip of the material, and that's lead to the final deformation or change in length of the material. So this type of dislocation is the main reason for the strength of the material. Okay, if we can remove the material, if we can remove the dislocation, or if we can arrest the movement of dislocation, then we can improve the strength. There are two possibilities. First one is remove the dislocations from the material. If there is no dislocation, we can say the material will have very high strength. So that is one possibility. Another possibility is resist the or restrict the movement of this dislocation. Maybe there are some dislocation, but if we can restrict the movement of this dislocation, then we can improve the strength of the material. So all the strengthening mechanism what we are discussing here is based on these factor. These are the 5 different strengthening mechanism. In all 5 strengthening mechanism, what we do is that we either remove the dislocation from the material or we restrict the motion of dislocation by using different mechanisms. Okay, so that is actually discussing in this strengthening mechanism. So the important factor for which depends the strength of a material is dislocation. Dislocation is motion. Okay. So since the hardness and strength are related to the ease with which a plastic deformation can be made to occur. By reducing the mobility of the dislocation, the mechanical strength may be enhanced. Okay, so we have to restrict the movement of the dislocation, thereby we can improve the strength of the material. Okay, so if we reduce the or restrict the movement of dislocation, then by using any mechanism, then we have to apply more force to initiate plastic deformation. For example, here we consider here in this material, I am applying a force. It is easily deformed, but I am taking another material. I apply force, but there is no deformation, visible deformation for this material. Okay, what it means? That means in this, there is no mechanism to resist the motion of dislocation. The dislocation can easily move on this material. Okay, finally a deformation is developed on this material. But in this material, this is very difficult to deform this material, or it's very difficult to move the dislocation along the material. Okay, we are using some mechanisms to resist the motion of dislocation. Okay, thereby we can improve the strength of the material. Okay, so here in this, we need to just apply very small amount of force for the plastic deformation. But here, for any type of plastic deformation, we have to apply very high amount of force. Okay, so this additional force is actually used to overcome the resistance of it against the dislocation. Okay, if we apply more force on this material will deform. So this additional force, what we applied on this material, used to overcome the resistance of it against the dislocation motion. Okay, by this additional force, this dislocation overcome the resistance and then they further move. Okay, thereby we can see a deformation on this material. So this is very important. The dislocation is the main reason for the which affect the strength of the material. Okay, so the more unconstrained dislocation motion, there is no restriction for the dislocation motion, then greater is the facility with which metal may deform. And that type of material will be very strong, softer as well as weaker. If there is no restriction for the movement of dislocation, then we can say the material is stronger, material is very softer and weaker. Or we can say the material will be more ductile. Okay, so this is the important point. Virtually all the strengthening mechanisms or techniques rely on this simple principle. What is the simple principle? Restricting or hindering dislocation motion renders a material harder and stronger. Okay, so for making a material which is very harder and stronger, what we do? We restrict the motion of the dislocation. We should not allow the motion of dislocation along the material. So there are different mechanisms to restrict the movement of dislocation. There are 5 mechanisms. Okay, so next I am going to explain what are the different mechanisms to restrict the movement of dislocation. Okay, so all the mechanisms actually I discussed in the last 2 modules. Okay, all the mechanisms are discussed. Just this age precipitation and dispersion hardening is not explained, but these 3 already I explained the previous modules. Just to recapitulate all the topics what we discussed in the last module. Okay, first one is grain size reduction. Grain size reduction. Okay, so here we have a first one is grain size reduction. Grain size reduction. For example, consider a single crystalline material. It's a single crystalline material. Okay, this is a single crystalline material. So, what about the arrangement of atoms? For example, this is the arrangement of atoms in the single crystalline material. This is the direction. Okay, there is no grain boundary. This is a single crystalline material. It is not a polycrystalline material. So the grains are arranged, or sorry, the atoms are arranged in a regular ordered manner for a long range order. Okay, so there is no grain boundary. There is no grain boundary. Okay, so for example, consider dislocation line here. Consider dislocation line here in this point. Okay, a dislocation line can be considered here. Okay, so if this material is regularly arranged and it is close packed, if it is very close packed, then this dislocation can easily move along the slip plane. Along the slip plane, the dislocation can easily move from this end to this end without any restriction. Without any restriction. Okay, so if you take another plane, for example, if you take in another direction, for example, this direction, here also we can see a dislocation line, he is here. This can easily move along the slip plane without any restriction, because the atoms are closely packed in a single crystalline material and there is no grain boundary of misoriented particles. So the dislocation can easily move in this single crystalline material. If the dislocation can easily move, then strength will be very low. So that
Weakened.
okay. Any doubt? Okay. So dislocation movement is very easy here. Very easy here. So strength will be low. That is the case of pure material. Pure material. Okay. For example, you take gold. You take gold. So pure gold is very weak in nature. So what we do to improve the strength of the gold, we add some impurities like a copper or any silver, any other impurities added to gold to improve the strength. So here pure material is very weak because the dislocation can move easily along the slip plane in case of pure material. But if as pure material as well as this single crystalline material, this is a single crystalline material. But for a polycrystalline material, we discuss how this polycrystalline material is formed. Different nucleus is formed during solidification process, and different nucleus is develop or growth in dendrite manner. Okay, we already discussed how this polycrystalline material is formed. Okay, so naturally polycrystalline material is formed, but by using any mechanism we can develop single crystalline material. So this is the orientation direction of the this grain. Okay, and I am taking another grain. Okay, this is another grain. So this is the orientation direction of the next grain. Okay, and in between we have a region. We have a region here where the atoms are loosely packed, as well as this is misoriented in this area. Okay, and the bonding, the atoms are loosely bonded with the adjacent atom. That area is called grain boundary area. Okay, so for a polycrystalline material, for example, a dislocation start in this direction. In this direction, a dislocation start. Okay, but this dislocation can easily move up to this grain boundary. Up to this grain boundary, the dislocation can move. But at the grain boundary region, we already studied the grain boundary region. For example, this is the grain boundary region. Here we have the orderly arranged atom. Here also another direction we have orderly arranged atom. But in grain boundary region, this is misoriented atoms we can see. Misoriented atoms like this we can see. Okay, so here the orientation is this direction, but here in the grain boundary region we can see orientation in different direction. So it is very difficult to propagate this dislocation by crossing this grain boundary area. It is very difficult because the direction of the dislocation line should be changed, as well as this here the atomic packing is very loose. So there needed extra force for the propagation of the dislocation along the grain boundary. Okay, even if it is cross the grain boundary, again we can see in the next grain. In the next grain, the orientation of the atoms is different. Here we can see the orientation is in this direction, but here we can see the orientation in this direction. The orientation is different. Again, some resistance is offered by the disoriented atoms or orientation in this grain. The orientation is in different direction. So that offers a resistance for the movement of dislocation. Okay, so such a polycrystalline material, because of the grain boundary and differently oriented atoms or grains, the dislocation movement is very difficult. Or we can say the polycrystalline material offer more resistance than that of single crystalline material. Thereby, we can say the polycrystalline material is stronger than that of single crystalline material. Okay, so grain boundary acts as an obstruction to the dislocation motion. Okay, so this grain boundary offer a restriction. So the dislocation can move easily, very easily up to this point. Can move up to this point very easily. But in the grain boundary region, the crossing of the grain boundary and the propagation of the dislocation in another direction, for that we need to apply more amount of force. We need to apply more amount of force. That means we need to apply more amount of force means the strength of the material is higher. Okay, so that is about the strength comparison of single and polycrystalline material. So we come to the conclusion that a grain boundary offer a resistance to a dislocation motion. So when we compare coarse grains and fine-grained material and coarse-grained material, which one has more grain boundary regions? When we compare these two, the volume is same, but this is a coarse grain and this one is a fine grain. We can see the more grain boundary regions or grain surface regions or grain boundary regions is more in this fine-grained material. Okay, so each small grains is surrounded by boundary. So net grain boundary will be higher for fine-grained material than that of coarse-grained material. Okay, so that means more grain boundary means more boundaries to resist the dislocation motion, or fine-grained materials are stronger than that of coarse-grained material. Okay, so here all the grain boundary offer a restrictions or obstacle for the movement of dislocation. Okay, so here grain boundary regions are more, so fine-grained materials are higher strength, has higher strength than that of coarse-grained material. Okay, so we already discussed Hall-Pitch relation. Hall-Pitch relation gives the relationship between the diameter of the grains, and the yield strength of the material. We can measure the diameter using different. We already discussed using a line method. We can measure the diameter. We initially measure the length of the line. Then we measure the how many grains intersect in this line, 1, 2, 3, 4, 5. So based on that, we studied two methods to determine the diameter of these each grains. Okay, so that diameter is this one, root d. This is the grain diameter. Okay, and this is the equation, Hall-Pitch relation, sigma y is equal to sigma infinity plus k by root d. So when we plot a graph between sigma y, yield strength and 1 by root d, we got a straight line. And the slope of this line is called k. That constant is the slope of this line. And sigma infinity is the another constant, which is the y-intersect of this line. Y-intersect of this line. And sigma y is nothing but it is the yield strength for a infinitely large. We can see sigma y is equal to sigma infinity when d is equal to 0. Okay, 1 by root d is equal to 0. 1 by root d equal to 0 means d is equal to infinity. D infinity means extra very large grain. Okay, so this y-axis sigma y. When sigma y changes to sigma infinity, when 1 by root d is equal to 0. 1 by root d equal to 0 means d equal to infinity. Okay, d infinity means the diameter of the grain. The diameter of the grain is infinity. The diameter of the grain is infinity means the diameter is very large, or we can say that is a single crystalline material. Okay, so that is sigma infinity is nothing but it is the yield strength of a single crystalline material, sigma infinity. So based on this equation, we can calculate the yield strength. And from this equation, it is clear that yield strength is inversely proportional to the grain diameter. Okay, yield strength is inversely proportional to the grain diameter, or strength is inversely proportional to the grain diameter, or we can say if the grain diameter or grain size is very small, then strength we can improve. We can improve the strength. So that is Hall-Pist relation. But this Hall-Pist relation only applicable for medium-sized grains. It cannot be used for very large grain as well as very small grains like in nanomaterial. We cannot use this relationship for nanomaterial. Okay, this is not applicable. So this Hall-Pist relation gives the relation between the strength and the size of the grain. If we can make a very small grain, we can improve the strength of the material. Okay, so this is the another diagram showing the how the dislocations are moving. So we can see the dislocation movement. See this one. The dislocation moving here. Extract half plane of atom ending here. Okay, so such type of dislocation is shown here. Such type of dislocation is shown here. From this point, this half plane, extra half plane moving up to this point. But at the irregular grain bound region, in the grain bound region, the grain boundary offer a very resistance to the movement of dislocation. Further movement is arrested by the grain boundary. Okay, so grain boundary acts as a barrier for dislocation because of two reasons. Since the two grains are differently oriented, when we compare the orientation of the grains, here maybe this is the orientation in this direction, this is the orientation, but here it may be in this direction. Okay, so the orientation is different when we compare the two grains. Okay, so dislocation passing into grain B, this is grain B. Okay, will have to change its direction of motion. This become more difficult as the crystallography misorientation increase. So we can say high angle grain boundary has more strength than that of low angle grain boundary. We have studied what is high angle grain boundary and low angle grain boundary. So high angle grain boundary means the orientation difference between the grain A and grain B will be very large. So high angle grain boundary, the motion transmission, dislocation motion transmission from grain A to B will be very difficult. Okay, so that is the first reason. The atomic disorder within the grain boundary region will result in the discontinuity in the slip plane from one grain to another grain. Already I explained, in this region we have some misoriented atoms, loosely packed misoriented atoms in the grain boundary region. So the dislocation slip movement along the slip plane cannot further move into the next grain because of this grain boundary atoms in the grain boundary regions. Okay, so high angle grain boundary dislocation tends to pile up at the grain boundaries. This pile up induce strength concentration ahead of their slip plane, which generate new dislocation in the adjacent grain. I will explain what is pile up later. So this dislocation pile up also a reason for the increase in strength of the material. Any doubt? Any doubt? Okay. So the grain boundary, small angled grain boundary is not effective for interfering the slip process, dislocation motion, because the misalignment will be very slight in case of the small angled grain boundary. So we have to make a high angled grain boundary for huge dislocation motion resistance. Okay, and twin boundary offer a effective block in slip and increase the strength. Twin boundary. We already discussed what is twin boundary. Okay. And of course, the boundary between two different phases are also impeding the movement of dislocation. This is important for the strengthening of more complex alloys. Okay, so far we discussed only single grain. For example, here the grain will be iron grain. Okay, everywhere the grain, each grain will be iron grains. Okay, in between iron grains, for a polycrystalline iron crystal material, a grain boundary is present. That grain boundary restricts the motion of dislocation. And similarly, we have another solid solution. In case of solid solution, within the each grain, we already discussed that. Within the each, for example, alpha plus Fe3C. We discussed about that, alpha plus Fe3C. So in alpha plus Fe3C pairwise structure, this is the corresponding figure. Here we have alpha solid phase, and then Fe3C, then again alpha, then again alpha. Okay, and in between, in this region, we have Fe3C. Here we have Fe3C. Okay, and this is called grain boundary. This is called grain boundary. This region. This region is called grain boundary. Okay, the separation between two grain. But within the grain also, we have phase boundary. We have phase boundary within the grain. What is that? The phase boundary between the alpha phase and the Fe3 phase. This is the phase boundary. This one. This region. Here, this region is a phase boundary. So within the grain, we have a phase boundary also. This is called grain boundary, or this is called grain boundary. And within the grain, we have phase boundary also. Okay, the separation surface between the alpha and Fe3C. There will be a separation. So that also offer a resistance for the movement of dislocation. So that is explained here. Boundaries between two different phases are also impediments to the movement of dislocation. That is important in the strengthening of more complex alloy. Okay. So by reducing the size, we can improve the strength. So that is the first strengthening mechanism, how the grain size affect the strength of the material. So we have to make a material with the fine grains for improve the strength. Any doubt? Any doubt? Okay. So next one is solid solution.
No, sir.
Okay. But next one is solid solution strengthening. So we already discussed about what is solid solution. Solid solution, we have two components. One is solvent and other one is solute. Okay, solvent and solute. For example, in case of iron carbon equilibrium diagram, in this region, we have alpha solid solution. In case of alpha solid solution, what is that? A solid solution of iron and carbon. Iron and carbon. This one is iron, and the carbon atoms occupy in the interstitial position of the iron. So this is a solid solution, alpha solid solution. And in this, we have iron that is solvent, and carbon that is interstitial impurity, carbon that is a solute. Okay, so this solid solutioning or alloying, this is another name is called alloying, alloy strengthening. We add an impurity into the base metal, so that is alloying. So, or we can say solid solution strengthening. Okay, so this alloying or solid solution strengthening improve the strength. We know the strength of the steel is very much higher than that of iron. So alloying steel is a solid solution, or alloy element or alloy material. Iron is a pure material. Okay, when we compare these two, we can say this alloy element or solid solution material has higher strength than that of pure element. Okay, so the solid solution is stronger than that of pure element. Okay, so how this solid solution improve the strength? Okay, how this solid solution improve the strength? Sorry. So here, in this case, the solute atoms, we add solute atoms here. In this case, we can see a solute atom, interstitial carbon atoms. So this is a pure material, pure, for example, pure iron. Okay, pure iron. In case of steel, this is a pure iron. It's not an industrial. So, okay. So this is a substitution solid solution is formed here. So here, this is a pure material, and I am adding an impurity here, a substitution solid solution. How the substitution solid solution is formed? This impurity atom, this is my impurity atom. Okay, this impurity atom occupy in this position by replacing this atom. This impurity atom, almost size is same. Okay, by adding this impurity atom, we have to obey the Hume-Rothery rule. Okay, so a solute atom or impurity atom which obey the Hume-Rothery rule occupy this position by replacing the parent atom. And this is the final substitutional solid solution. So what happened when impurity atoms or substitutional solute occupy this position? There will be some atomic distortion. Okay, here we can see the atom this atom, if we consider this atom initially at this position, in the normal position, move by some amount here. You can see a extra edge here. You can see some extra edge here. That means this layer of atom move towards the left for occupying this higher size solute atom. Similarly, these two atoms also move towards this direction to occupy the bigger size substitutional solute atom. Or we can say in this region, here, of course, in this region also we can see a shifting. And here also in this region, there will be a stress field or strain field. Stress field or strain field will be developed. Okay, so by this impurity atom addition in this substitutional position, in this adjacent atom experience a strain field or stress field. They experience a stress or strain. Okay, because this is a normal position of atom. With the lower energy state, they occupy in samadhana. But by the introduction of this substitutional atom, idella ee direction move cheyidu. Move cheyumba actually adiloru stress develop cheyana. A stress is developed. Correspondingly, a strain is also developed in this adjacent atom. Okay, so a stress field or strain field is generated on this adjacent atom. Okay, so that is explained here in the pure element. By the addition of this substitution element, a stress field is generated. We can see this direction. A stress field is generated. Okay, in this direction. And similarly, if for a substitutional interstitial atom, for example, this carbon atom occupying the interstitial position of the iron, what happened? Similar case will develop here also. When in the interstitial void space, when we compare the interstitial void space and the size of this interstitial atom, the interstitial atom has higher size than that of interstitial void space. So when an interstitial atom occupy this position, this atom offer a stress on the adjacent atom. Okay, when this black color atom, interstitial atom impurity, occupy this position, void space region, this atom has higher size than that of the interstitial void space, and this atom offer a stress around this stress on this adjacent atom. So here we can see a movement of these adjacent atoms into the surrounding. Okay, or stress or corresponding strain is developed on this adjacent atom. Okay, so a stress field or strain field is around the solute atoms is produced, and this strain field interact with the strain field of the dislocation and impediment in the dislocation motion. Okay, so this strain field, stress field or strain field offer a resistance for the movement or dislocation. This offer a movement or dislocation. How this stress field or strain field offer a resistance? So here in this case of edge dislocation, okay, for example, in case of edge dislocation, here we have an edge dislocation. So this is an edge dislocation. We can see an extra layer of atoms here. This is an extra layer of atom. This is the slip plate. This is a slip plate. Okay. So, for example, solute atoms occupy in this position. It may be an interstitial solute atom or substitutional solute atom. Okay. So, a solute atoms occupy this position. Okay. So, these solute atoms offer a strain field or stress field around this solute atom. A stress field or strain field is developed around this solute atom. Okay, and this dislocation line has a stress field also. It has also a stress field or strain field. It may be tensile or compressive. Okay, so this dislocation, this edge dislocation has a stress field or strain field, and it may be tensile or compressive. So when this dislocation line move in this direction, what happened? This solute atom also offer a stress field that is also maybe tensile or compressive. Okay, so when they come closer, if both are tensile, what happened? The stress field developed by the solute atom oppose the stress field of this dislocation line. Okay, the stress field created by this solute atoms, we already discussed how this stress field is developed by substitutional impurity or interstitial impurity, and this may be tensile or compressive. If this stress field is tensile and the dislocation line also has imperfection, so that imperfection also has a stress field that may be tensile or compressive. If both are tensile, they offer a repulsive force. So this dislocation has to overcome this stress field for the further movement in this direction. Okay, the dislocation has to move further. For that, they have to offer or overcome the resistance offered by the stress field of the solute atom. If both are tensile, for example, if both are different, one is tensile and one is compressive, then of course this stress field attract this dislocation stress field. Both are different in sign. One is tensile and one is compressive. So solute atom stress field attract the dislocation line stress field. So both attract, come closer. But after that, after closing, if the dislocation wants to move in this direction, that will not movement restricted by this solute stress field. What is the reason? Both are same sign, opposite sign. There will be an attractive force. So this stress field offer a resistance against the further motion because of the attraction. So even if it is in same stress field, tensile and tensile or tensile and compressive, this stress field created by the solute atom offer a resistance for the movement of dislocation. Thereby, the dislocation motion is arrested by the substitutional as well as interstitial solute solution. Okay, so this is this stress field interact with the stress or strain. We can say anything, strain field or stress field. The strain field interacts with the strain field of the dislocation. The interaction may be repulsive or attractive. If it is repulsive, these two stress field oppose the movement when they come closer, and if they are attractive, oppose the movement when they gone apart. Okay, gone away. So that thereby we can restrict the motion of dislocation. That is the solute solution strengthening. Any doubt? Any doubt? Clear or no?
Yes, sir. Clear.
Okay.
Clear answer.
So this is the substitution solute solution interstitial solute solution is stress field create. A stress field dislocations in the movement and the motion arrest. Okay, that is the main core of this solute solution strengthening. So that is actually doing in alloying. We impurity add for example, gold impurity add copper or silver add. Iron impurity add carbon add. Impurities add strengthening mechanism. Steel has higher strength than that of iron. And the main reason is that. Okay. In a substitutional or interstitial solute offer a resistance for the movement of dislocation. Next one is work hardening or strain hardening. This is a very important topic. Work hardening or strain hardening. Okay. So this topic is interval 10 minutes. This is better class. കുറച്ച് ടോപ്പിക്സ് ഉള്ളൂ ഇവിടെ വരെയുള്ളൂ പെട്ടെന്ന് തീർക്കുന്ന ഈ മെക്കാനിസംസ് പറഞ്ഞാൽ മതി. So next one is work hardening or strain hardening, or another name is called cold working. So what is work hardening or strain hardening? So by offering large amount of deformation on the material, we can improve the strength. For example, here in this material, I am applying 10 Newton force. Okay, and the cross section, for example, is equal to 1 centimeter square. So stress will be 10 Newton by 1 centimeter square. Okay, that is the stress applied on this for the deformation. So when I apply this much amount of stress, the material move or deform easily. It's deform easily. Okay, and this plastic, we apply some force or stress, and by applying the stress, there will be some deformation on this material. There are some deformation on this material. Okay, there are some deformation, and this deformation is called cold working or strain hardening or work hardening. Okay, so work hardening or cold working, this is called cold working. Okay, so we apply some force on this material at a room temperature or below recrystallization temperature. That means that not at the hot condition. We apply this force in this material at a room temperature or normal atmospheric temperature or below recrystallization temperature. Okay, the material is not in the red hot condition. So in that condition, I am applying some force or stress. The material is plastically deformed. Okay, and this plastically deformed material has higher strength than that of the undeformed material. Okay. So when I apply stress on this material, it is deformed by an amount, and this deformed material has higher strength than that of undeformed material. That means, so initially I apply sigma amount of stress, sigma 1 amount of stress for deformation. But after a particular amount of deformation, if I apply again sigma 1 amount of stress, there will not be any deformation. We have to apply a stress which is greater than sigma 1 for further deformation. That means a deformed material has higher strength than that of undeformed material. Okay, so the strength of deformed material is higher than that of undeformed material. And this is called strain hardening or work hardening. By working on this material, I am applying some force and deform this material. By working on this material, I can increase the strength of the material. That is called, or by introducing some strain on this material or deformation on this material, I can improve the strength of this material. That mechanism is called work or strain hardening or cold working. Okay, the cold working name is because we apply the stress in the normal condition, normal temperature. Okay, so strain hardening is the phenomenon whereby ductile material becomes harder and stronger as it is plastically deformed. So when we plastically deform, it becomes more stronger and harder. Sometimes it is called work hardening, because the temperature at which deformation takes place is cold, relatively cold, relative to absolute melting temperature of the metal. So we can say this is a cold working also. The temperature where we apply the deformation is normal temperature or cold compared to the melting point of the metal. Always we apply below the melting point or below recrystallization temperature. Okay, so thereby we can improve the strength. That is called strain hardening. So, and we can see an example here. In this example, I have already explained this example in the last lectures. So here I am taking a material. Okay, this is my workpiece, and in this material, this is strain, this is stress. I am applying UTM testing. So initially, the proportionality limit is reached and yield point is reached. This is the yield point. Okay, sigma y, yield point. After crossing the yield point, the material is permanently deformed. Okay. So this is at this point I stop this experiment. This is not a fracture point. We have further increase. We can further increase. So this is the fracture point. But I stop the experiment at this point. Okay. So from this point to this point, this material undergo a plastic deformation. So this is the final shape of the material after this plastic deformation. Okay, there is an increase in size of the material. Length is increased. From this point to this point, the length is increased and diameter is reduced. Okay, so this is the yield strength of the material, the strength required for the stress which is required for the plastic deformation. Okay, and what is the corresponding strain? Corresponding strain or deformation? This much is the corresponding strain. Okay, we apply sigma y, above sigma y stress. Correspondingly, this is the amount of deformation or strain. Okay, this much is the amount of change in deformation. This much. Okay, again, I am repeating this experiment with the this is my sample. In this experiment, this is my sample. That is the deformed material. In this experiment, this is the undeformed material was my sample. But here in this experiment, the deformed, what I get from this point, okay, the sample at this point is used for this experiment. Okay, so I repeat the experiment with this sample. Again, the stress is increased, but this material starts to plastically deform, not on the same sigma y, but the yield strength is this one, sigma y dash. Okay, the plastically deformed material yield strength is this point. That means after this point only the material is plastically deformed. Okay, so we can say the yield strength, the sigma y of the deformed material, the sigma y dash, that is deformed material. Deformed material is higher than that of yield strength of the undeformed material. It's very important. This is called work hardening. Okay, so deformed material has higher strength than that of undeformed material. Okay, so I am making a connecting rod. I am making a connecting rod by casting process. Same connecting rod with the same material by forging process. This is by forging process. This one by casting process. Which one has higher strength?
Forged one.
Forged one. What is the reason? Yes, forged one is actually a plastically deformed workpiece. So in forging process, what we do, we kept this raw material on a die and we apply a compressive force, and this workpiece changes to connecting rod shape. But this casting process, we solidify the molten material. Okay, so there is no plastic deformation for casting, but here we have a huge amount of plastic deformation. So by this plastic deformation, the strength of the deformed material is increased. Strength of the deformed material is increased than that of undeformed material. So forged component has higher strength. Okay, so that is called strain hardening. And what is the reason for this strain hardening? Deformed materials are higher strength than that of undeformed material. What is the reason? The reason is this: the dislocation interaction. Dislocation interaction is the reason for strain hardening. Okay, this is the reason for strain hardening. So when I deform a material, so this is the initial material. After plastic deformation, strength is size is different. Okay, but when I plastically deform, lots of dislocations lines will be formed in this material. Okay, initially we have only 2 or 3, for example, 2 or 3 dislocation, but after plastic deformation, number of dislocations lines increased. What is the one reason for this increase of dislocation lines? Anyone? What is the main reason for the increase in dislocation line during plastic deformation?
Frank Reed source. Sir, Christo Kurian Varghese.
Okay, so main reason is Frank Reed source. Okay, by plastically deform, each dislocation multiply and number of such dislocation is formed. Okay, so when number of such dislocation is formed, actually we know dislocation is an imperfection. It's a line imperfection. Okay, when the number of dislocation lines increase, that means the material should weaken. Material should be weaker. Weaker material. It should be weaker material, because when we compare these two material, undeformed and deformed material has higher number of dislocation lines. That means higher value of imperfections. Then the material should be weakened. It should be weaker one. But the material is stronger. Experimentally prove that deformed material is stronger than that of undeformed material. The reason is that how this material becomes stronger. Here we can say the material should be weaker, but experimentally we prove that deformed material is stronger. The reason for this strength of the deformed material by strain hardening is called dislocation interaction. Dislocation interaction. Okay, so what is dislocation interaction? The mobility of the dislocation, during strain hardening, workpiece is deformed. During deformation, dislocation density increase. Here we can see per volume or per number of dislocation lines length per volume is higher here. So dislocation density increases. As the dislocation density increases, dislocation will act as a barrier to each other. This is very important. Dislocation will act as a barrier to each other. In the previous case, how we restrict the motion of dislocation, here in this case, a solute atom restricts the movement of dislocation here. But here, in this case, one dislocation line restricts the movement of another dislocation line. So this type of interaction, that one dislocation line restricts the movement of another dislocation line. Okay, so that is very important. As dislocation density increases, dislocations will act as a barrier to each other. One dislocation line offer a resistance to another dislocation line. Thereby, complete dislocation motion is arrested. Thereby, we can improve the strength of the material. This is the reason. So actually, by deformation, the dislocation density increases, but this dislocation density increase not affect the strength of the material, because all the dislocation offer a resistance to any other dislocation. But here it is not the case. When for example, when this dislocation moves in this direction, there may not be any dislocation in this direction to offer a resistance to this dislocation. So it can move from this point to this point easily, because dislocation density is very small here. So without any interference with another dislocation, it can move from, the probability is high to move from this point to this point. But when we compare this dislocation, here the dislocation density is very high. So when it moves from this point to dislocation, the probability of finding another dislocation which resists the motion of this dislocation is very high. Okay, so thereby the strength is increased. So on the average, dislocation strain interactions are repulsive. The net result is that the motion of the dislocation hinders by the presence of another dislocation. Okay, one dislocation resists the motion of another dislocation. As the mobility of the dislocation hindered, strength will increase. Okay, so interference by other dislocation for the motion of given dislocation is the reason for the increase in strength, and dislocation motion will be very difficult. So we can see the case of different cold working of low carbon steel. 0.0%, 0%, 4% cold working, 24% cold working. 24% cold working means by plastic deformation, I increase the size by 24%. That is 24% cold working. We can see the graph. By 24% cold working, the yield strength is improved. This is a stress strain graph. You can see the increase in the yield strength of by different value of cold working. Without cold working, undeformed material, this is the yield strength, 250. But by cold working, it is increased from 250 to around 600. That is the difference, or that is the importance of strain hardening to improve the strength of the material. Okay, so this is these two graphs are superimposed here. Both are same. Both are same. These two graphs are, this is loading, then unloading, and same unloaded material again loaded. So this is showing these two graphs are superimposed in this picture. Okay. Do you want to know the reason for this dislocation interaction? പറയണോ ഞാൻ ജസ്റ്റ് ഒന്ന് പറയാം. ഇതൊന്നും ആവശ്യമില്ല, ഞാൻ ജസ്റ്റ് ഒന്ന് പറയാം. ഓക്കെ, ഈ സംഭവം ആവശ്യമില്ല. നിങ്ങൾ എന്തുകൊണ്ടാണ് ഈ ഡിസ്ലോക്കേഷൻ, അതായത് വൺ ഡിസ്ലോക്കേഷൻ ലൈൻ restrict the movement of another dislocation line? What is the reason for that? The same which we discussed in the case of solute, a stress field. That is the reason for that. So here it is somewhat complex, not required. Just for understanding how this dislocation interaction restrict the movement of dislocation lines is explained here. This is just for understanding and not required. Detail at and this is a FCC QC structure. In the FCC QC structure, the favorable slip planes are 111. Okay, favorable slip planes are 111 family. That means these are the slip planes. Okay, so in this slip planes, dislocation can easily move because in this slip planes atoms are closely packed. Okay, so in this slip plane, I am taking two slip plane 1-11, 1-1. So these are the red color and green colors are those two slip planes which are favorable for the slip movement. Okay, so I am taking that two slip planes. I'm taking that two slip planes. This is my first slip plane. That is this 1-11. This slip plane. Okay, that is this one. Another slip plane is this one. So this one is 1-11 slip plane, and this one is this 1-1 slip plane. Okay, so these are the two slip planes we can see in the FCC crystal structure. For example, there is a dislocation in this slip plane. This is a dislocation in this slip plane. And another dislocation we can see in this slip plane. This is another dislocation. Okay, and these two dislocations moving in this direction. These two dislocations moving in this direction. Okay, so this dislocation when moves in this direction, they may come and join together in this point. These two dislocations join together in this point. Okay, and we got a resultant dislocation. This is very simple manner. I am not explaining the Burgers vector and all this energies associated with the dislocation. This is simple reason for this dislocation interaction. So these two dislocation lines join together, or a resultant dislocation lines is produced here. Okay, but this dislocation line is on another plane. Okay, this dislocation line is on another plane. For example, this dislocation line is in this plane. Sorry, in this plane. This dislocation line, or this dislocation after the resultant dislocation line is in this plane. In this plane. Okay, and this plane is that is 001. This plane is 001 plane. Okay, and these two planes 1-11 and 1-1 are favorable slip plane for dislocation movement because the atoms are very closely packed in these two planes, so dislocation can easily move. But after joining the final dislocation, which is on 001 plane, this plane is not a favorable slip plane. Okay, this is not a favorable slip plane. So this final dislocation cannot move further because this is in the 001 plane, which is not favorable for further movement of dislocation. So thereby the dislocation, by the interaction of these two dislocation, a immovable dislocation is produced. So that is the one reason for of dislocation interaction increase the strength. So this dislocation cannot move because this is in the immovable or not a favorable slip plane. So here it cannot move. Here it cannot move in this direction. In this direction it cannot move. It's very difficult. It is not closely packed. So that is the one reason. Another reason is that, so for example, such a higher energy dislocation line is present here. This is the higher energy dislocation line. Any further, so by the addition of these two dislocation, in this dislocation has higher energy. It has higher energy. So when addition, another dislocation line, this is not this dislocation line, it's already joined here. And another dislocation when try to move here, or another dislocation when try to move in this direction, this dislocation has higher energy than that of these two, because this is the after product of joining of these two dislocation lines. So it has higher energy. So of course this dislocation restrict the or repel the movement of this dislocation in this direction. Okay, this higher energy dislocation line restrict the movement of this as well as this dislocation in this direction. So it is act as a traffic jam. It acting as a traffic jam. Further dislocation motion is not possible in this direction and this direction. So there are number of dislocation is accumulated here, or another name is piling up. This is called dislocation pile up. Pile up. Dislocation pile up is produced because of the traffic jam produced by higher energy dislocation. Okay, this dislocation restrict the movement of all the or repel the movement of all the other dislocation. This is a favorable slip plane. These two are favorable slip plane. So there are lots of dislocations in this plane, but the movement of this dislocation on these two plane is restricted by this high energy slip, high energy dislocation. So there are number of dislocations accumulated here. This is called dislocation pileup. And this dislocation pileup is also a reason for there is no dislocation motion or strength is improved. So these are the two reasons for the improvement of strength for a deformed material or by strain hardening. Understood? Any doubt? And this is called the dislocation cannot unable to move. That is called sessile. That is sessile movement of dislocation. It cannot further movement of dislocation is not possible. And this is called dislocation pileup or sessile movement of dislocation. Any doubt in this? This is for just for information. Okay. Any doubt? Okay. So you 10 minutes in interval either 10:35. 11 out the stop Viva session. If you have doubts, stay back here. Interval 10 minutes.